chapter 5 is all about electrons. But before we can talk about electrons, we have to do a little refresher on light. So with Rutherford's nuclear model, it wasn't complete. I mean, it was definitely better than J.J. Thomson's, but it didn't explain the location or the behavior of electrons. And so before the 1900s, it was thought that light particles behaved very similar to a wave. So there was a lot of research put into the electromagnetic radiation spectrum. And this is a form of energy that exhibits wave behavior. And that's as it moves through space. It can move through a vacuum. So by vacuum, I mean like space. And it moves at a constant speed of 3 times 10 to the 8th meters per second. So this is really what we call the speed of light. And it would be probably in your best interest if you somehow get that committed to memory. So the electromagnetic spectrum is all the forms of electromagnetic radiation. And we've talked about these before. With the shortest wavelengths, we have radio waves, all the way up to gamma rays with the shortest wavelengths and the highest energy. And so what we really are going to focus on here is just the different parts of a wave, specifically the wavelength. And this is the distance between two corresponding points on adjacent waves, or adjacent would be another way of saying waves that are side by side. The frequency, we look at the number of cycles that pass a certain point in a specific amount of time. Usually it's measured in the number of cycles per second. And so when we have one wave per second, we call that unit a hertz. And so we have this formula, C equals wavelength times frequency, where C is the speed of light, which is at 3 times 10 to the 8th meters per second. So we've done some problems before with this formula, but we'll just practice another quick one here. The color orange within the visible spectrum has a wavelength of 620 nanometers. What is the frequency of the orange light? And so whenever we do these problems, because the speed of light is in the unit meters per second, we have to get all of these wavelengths converted into meters before we can do any work with the formula. So we'll have to just take 620 nanometers, use the railroad tracks, 1 nanometer, and from your pink sheet, a nanometer is 10 to the 9th meters, and you'll get 6.2 times 10 to the 11th meters. Now that your wavelength is in meters, we can use the formula C equals wavelength times frequency. And if you remember from 9th grade, that lambda stands for wavelength. So we know the speed of light is 3 times 10 to the 8th meters over second. Our wavelength is 6.2 times 10 to the 11th meters, and multiply it by frequency to find the frequency. So divide each side by 6.2 times 10 to the 11th meters. 6.2 times 10 to the 11th meters. The meters cancel, and we're left with a frequency of 4.84, and the units on frequency is hertz. HZ is the appropriate abbreviation. So in the 1900s, a German scientist by the name of Max Planck studied the emission of light by hot objects. So we know that hot objects, when they get really, really hot, they glow and they give off light. And what he discovered was that the energy of a hot body, and here we're talking body meaning a hot object, could only be lost in small discrete amounts. By discrete, what we mean is defined amounts. It couldn't be lost in like 1.5 of something. It had to be 1, 2, 3, 4. There was no in between. And so this led to the development of the idea of quantum. And this is the minimum quantity of energy that can either be lost or gained by an atom. So a way to think of this is to, if you look at the brick wall, each brick would equal one quantum or one quanta of that wall. That wall, in order to build it up or take it down, you can only build it one brick at a time or take it down one brick at a time. And so Max Planck has a formula, E equals the frequency times Planck's constant. So here's Planck's constant for you. And E is representing the amount of energy. So E for energy. So Einstein kind of liked this idea of quantum, and in 1905 he proposed that light could be described as quanta, or discrete units. And he said that the light not only was like a particle or a quanta, but it behaved like a particle and not like a wave. And so he called these photons. These are particles of electromagnetic radiation. It has no mass, and it carries a single quanta of energy, a single amount of energy. And so this led him to the discovery of the photoelectric effect. And this is a phenomenon that occurs when light, when it gets shined onto a metal surface, causes the ejection of electrons from that metal. And this will only happen at certain frequencies of light. If the frequency is too low, no electrons will be ejected. And this is regardless of the intensity of the light. If we have a high enough frequency, the electrons will be ejected and will shoot off. So if we increase intensity, the more electrons will be removed. So if we look at the diagram, we can see here red. Red actually is a fairly low frequency. And you can see that nothing is bouncing off this piece of metal. This is metal down here. However, if we increased our frequency a little bit, green has a little higher frequency. And so now there's enough frequency to remove a single electron and shoot it off of that piece of metal. And same with violet or purple, it has a very high frequency, and so it also has the ability to shoot off electrons. And so we call this the photoelectric effect. And we see these photoelectric cells, they get used to power our calculators. And so the little, if you have one of those calculators that's kind of like almost solar powered, and you'll see like off to one side there'll be like a little rectangle with almost 3 other squares in it, and it's darkened. And if you put your thumb over it, your calculator seems to die. That's because it needs that light to provide some energy to remove some electrons so we can power that calculator. So for a sample problem, what is the energy of a photon of green light when it has a frequency of 5.75 times 10 to the 14th hertz? And so this is the formula where we're going to use Planck's constant, which is H. So remember E for energy and Planck's constant. And lastly, this V is for frequency. So we don't know our energy. Planck's constant from the previous slide is 6.626 times 10 to the negative 34th. And our frequency is given to us in our problem, 5.75 times 10 to the 14th. And when you multiply that all together, you'll get 3.81 times 10 to the negative 34th. And because it's energy, our unit is the joule. And so this has kind of been a mix of review and a couple new concepts about light and quanta. And tomorrow's video will continue on with these ideas.